So now that you've gained an intuitive an intuitive understanding of what quantization is trying to do, the simple fact that it's trying to maintain this relative distance in between these points, all while constraining them down and scaling them down into a range that's supported by our target data type, in this case 8-bit precision. And then once we've got these numbers scaled down into this range, it's very easy just to cast them to int8 using PyTorch or whichever package you're using. Now, obviously, there's a formula for doing this. I want to first explain the formula, and then I want to go a step by step, and after this, to explain how some of these parameters like the scale and the 0 point are actually derived, so that you can appreciate sort of how mathematicians or people in this field came to these formulas and how they derived them. So first and foremost, the quantized value, any of these values that are in the quantized range here, they are going to be equal to the original value, the associated original value. So this one right here is going to be equal to the associated original value divided by a scale parameter and then shifted by a 0 point. And so if I take this number right here, this dot right here, let's say it's -500 or whichever number, I divide it by the scale that we've derived for all of these points of numbers. I'll show you how to calculate that later. And then I add to that the 0 point. I'll get this number right here in the quantized range. And so that's how you quantize a number. You divide it by the scale parameter, add the 0 point, and then you get the quantized number. To go back, because you want to go back, because if we don't have hardware that supports integer arithmetic with lower precisions than 32-bit or 16-bit, then we have to go back up first, right? And I'll show you later why that's the case. But so you're going to want to dequantize. So we showed you how to quantize it. We want to be able to dequantize it. To dequantize it, you're going to take the scale right here, and then you're going to multiply it by the quantized value minus the 0 point. So you take the quantized value, subtract off the 0 point, and then you multiply it by the scale. And then you get back to the original value, the original 32-bit in our case. And so the biggest thing here is, how do you get, we know where R and Q comes from. R is just this value right here in our original data type. And then Q is going to be the end result. That's what we want to get. But how do we get this scale and 0 point? How do we get these values? I'm about to show you that. So let's hop over to the whiteboard. All right, so how do we get this scale and 0 point? So I'm going to write down this equation. This is the equation for the dequantized step. This is taking our quantized value and getting it back to its original value in its original data type. In our case, it was taking the 8-bit quantized value and getting it to 32 bits. And so what we want is we want to find the scale and the 0 point. Now, if you're thinking about just rearranging this equation to solve for the scale and 0 point, it won't work. You'll wind up getting two sets of equations that are dependent upon each other. And so S will depend on Z and Z will depend on S, and that doesn't work. So what you have to do is you have to use a little bit of an intuitive understanding of how quantization works and come to the realization that these two statements are true. That the minimum value in the quantized value set is going to be equal to the minimum value in our original array or value set scaled or quantized. So the minimum value in our quantized array, so remember we have three numbers here and then we have three numbers here. The minimum value here is going to be equal to this one scaled down. And so that is what I mean by that. And so I'm going to do that. And then also, likewise, the maximum value in our quantized range is going to be equal to the maximum number in our R array divided by S plus Z. Okay, and so now if you want to get S and also subsequently to get Z, what you need to do is I'm going to subtract the min equation from the max equation. So I'm going to do q max minus q min. I know I wrote them like this one on top, this one on bottom, so that's a little confusing. But I'm going to do q max minus q min. And so q max minus q min is going to be equal to, well, the z's are going to cancel out no matter which way you order this equation. It's going to be equal to r max minus r min all over s. And if you want to do some arranging here, you got to bring s to the side by multiplying it on both sides. And that's going to be equal to r max minus r min. And then you're going to divide through by q max minus q min. I'm not going to write this out, but you're going to wind up with r max minus r min over q max minus q min. And so this right here, this right here is our equation for the scale. And then now the 0 point is pretty easy. The 0 point is just, you can take this equation right here and just rearrange it. And so that's going to be, z is going to be equal to q min minus r min over s. And so I wanted to show you this because this is how we came to the scale and 0 point. Also, this right here was not obvious to me in the beginning, and so I wanted to work through that to show you how we got the scale and 0 point before we go off and actually start quantizing values. So you should have a really detailed understanding of quantization at this point.